All right. Good. So, thank you so much. The human body is an amazing robot. We are fast, we are agile, we repair ourselves if we break, which is every roboticist's dream. We are powered just by random stuff from our environment. We can interact with this environment in a very fast and agile way, and we're completely silent. So, who wouldn't want to have a robot as good as a human body? And in the way of getting there, we can solve problems like people in a wheelchair, or how to regrow tissue, or actually building full replacement organs. And at some point, of course, upload their bodies or brains to robotic bodies. So this is the vision of the Roboy Project. We want to build robots as good as the human body in order to get there and solve a lot of important problems on the way. So it's basic research, commercial applications on the side. And this has started more than 10 years ago with Edge and Kronos, which were robots that followed the idea that if I'm building a robot that has muscles and tendons like the human body, it would then potentially generate consciousness. While this didn't come through, it sparked a range of robots that are continuously imitating the structure of the human body. Continued with something more engineerable, and in 2013, Roboy was born. Roboy was an amazing showpiece. The world loved it because it was probably the cutest humanoid robot in the world. And now, 5 years later, it's not only cute, it's actually an amazingly good robot. And how do you get there? So you need three critical components. You need a right team with the right processes and the right technology. So we're going to look a bit into this. How do you build the right team? So the Roboy team comprises of researchers, but also of more than 50 students at TU Munich, and it's very interdisciplinary. Robotics is very interdisciplinary, it's always interdisciplinary. It means we need mechanical engineers, electrical engineers, computer scientists, we even have biologists, we have medical people, we also have, of course, economists. We run this project, although it's a research project, like a company. We split into 5 different tech competence centers. We call them guilds. First, mechatronics. These are those guys that actually build the physical representation of physical robots that you can actually see at the outdoor schools right now. The middleware team develops its own electronics. The control team makes its electronics movable, and the cognition team works on the ability of you to interact with the robot, to talk to him, so you actually can see, can recognize. And last but not least, because we love technology and we always want to experiment, we always want to be at the very forefront of what's new, we have a growth team where we just explore new technologies like augmented reality, virtual reality, simulations, games, and so on. So, and we're structured into small project teams, and they're interdisciplinary. So while we have these competence groups, they never kind of work together in team for a certain project, but the projects are interdisciplinary. What you're seeing here is the Alpha to Omega team. With its task for this semester to basically hunt all the bugs that we find throughout the fair, throughout the usage of Roboy 2.0. And it already implemented first fixes throughout the fair. So we found a few things like the tendon in the shoulder was rubbing or falling off its current guidance, and Yuri sort of designed and implemented a fix and is already deployed. So this is sort of our normal iteration speed. So once you have the right team, you need the right processes. And with processes, I mean mindset. Because this is a chaotic world, it's not getting slower, it's getting faster. So we don't have time to communicate and roll out complex processes. We need people who have the right mindset at their core, who are agile, but are not chaotic agile. So often agile is meant, okay, we throw away all the processes, we do something. And it ends up just as bad as if we're following a Clara waterfall process, which you still end up in the wrong place. So how do you get to the right system of agility that allows you to continuously and efficiently arrive at the right destination? Well, we had developed a process at Technical University of Munich that is able to generate from a team that doesn't even know each other in the beginning of 2 weeks. After 2 weeks, they come up with a prototype like this, which is a robot that's able to clean windows, a functional prototype, a working business model, first customers who sign a letter of intent that they want to have this robot, and a done feasibility study so they know they can build this and develop this into a real product. Or a social beer sharing platform. And again, this is 2 weeks. After 2 weeks, they did this video. Or a prototype for a safe transport for children on bikes. Or a physical implementation of a virtual game that we all know and love, Mario Kart, with actual cars, but virtual playing fields. All of this is done in a course that's called Think, Make, Start. We run it at Tech University of Munich. We've run it now for more than 7 times, and we've continuously improved it over every iteration, and it's pretty good. Not only do students say it's the best course you can choose at Tech University of Munich, there's even people who go to Tech University of Munich just because of that course. And there's people that say, and they do this with all their passion in front of our students, that it changed their life. And they did so because they're now founders of companies that do well, founders of companies that win prizes such as the ISPO Brand New Award, just 3 months after Think, Make, Start. So they created their company, and 3 months later, they won the first awards. So this is Think, Make, Start, and we run it with corporates as well, because it's an innovation process that works, and we can show it. So it's called Tough Agile Framework. It's a framework that makes you look at your product from a customer's perspective, from a technical perspective, and from a business perspective, but in an integrated process that allows you to build the right product before building it right. So how does this look at an implementation in Roboy? So first of all, it's very prototype driven. This is the first prototype of Roboy 2.0. It's not a joke. And it's actually a very efficient prototype. It took about 2 hours to build the different teams. The left one is from the Mechatronics team, and the right one from the Middleware guild. So, what can you see? You can see that the robot consists of muscles, comprises 9 of them in the shoulder. After this prototype, everyone looking at this robot immediately knows where to place which mechanical part. For the electronics team, they visualized all the tendons, all the cables that had to be routed throughout this robot. And it's a mess. And that communicates very efficiently that we have to think of cabling. And the middleware team knew early on that cabling will be an issue, because of the mechatronics team visualizing this very quickly. And it also led to a very fast fail. So we wanted to put sensors all over the robot that allow us to track the robot from externally with the HMI Vive headset. We rebuilt these sensors, but we realized we can't do the cabling. So we postponed it until we find a solution like 3D MID that allows us to solve the cabling problem. Also, the second first priority is that we have very transparent communication. It all is messenger based, so Telegram, which is very fast, but we also use the Autodesk 360 app because it allows me to, wherever I am, basically look at CAD models and be like, okay, this was a good idea, let's do this a bit differently, very quickly, wherever I am. So really unblocking people. My biggest goal is to prevent someone being blocked by my inaction. And it should be, and it's the goal of everyone at Roboy team, to basically unblock and enable people, never be in the way, rather help. The third priority, number 1, is to document. We have to document a lot because my students are of course leaving because at the end of their masters, they are at the end of their excellence, of their studies, of their theoretical learning phase, but then they leave. And we have to document a lot so we understand after a while how we got where we are, what we learned on the way, and for others to get on board. Actually, we do hackathons, like 2 days sprints, where people work with the robots just to learn how to use them. And it works very well. And I would love to know which robots in here you can actually use to their fullest in 2 days. So, once you have the right mindset and the right team, of course you need the right technology. And we all love technology, so what we've done, of course, is not just build this robot, but build many robots on the way. So we built robot's legs. We actually had more complex legs in the beginning. We realized they're too hard to control right now, so we built crab-like legs, which only walk sideways, but allow us to explore on the stability of such a system. We have very simple systems that allow us to understand the dynamics of those muscles, and we have also more complex systems like prototypes of the arm. We then build the prototypes, and then we started building the second generation of Roboy. So this is April last year, so less than a year ago. Well, pretty much a year ago, and we spent a lot of time waiting for parts, which was not 2 hours. What we have is an agile systems architecture. It allows, we just defined at the very beginning, because once we did a geometrical prototype that sort of visualized where to put what, that it will be a mess if we just continue like that. People were sort of fighting with each other where to put their things. So we clearly defined connectors and how to work with them. And there were surfaces, like the red ones, you cannot change them. The yellow ones, there can nothing be adjacent to them. And the white ones is the ones we're able to connect to. So with this, we very efficiently, very quickly, in less than 3 months, had the full-blown CAD model that we then started building later on. And building we did, and of course we made sure that our products are CAD-proof and work. We built new muscles, smaller muscles that are very compact and produce about 300 newtons of force, although they're just small. And they were the series lactic actuators. And we use Autodesk generative design. To some extent, this is for us the critical technology. Because what we can do now is define just the constraints for a product and not the actual shape. So this part, it's only about 800 grams, but it has to hold all the forces in the robot, and the robot is about 80 kilograms. So we have a bending moment here of more than 140 newton meters, and this piece holds. We define that the attachment forces for the tendons to be a certain amount, and then that we need some space to mount the leg motors, and then we let the AI run. And we get a lot of options, and we can choose the one that was most aesthetically pleasing, or in this case also the one that was the most stable for cases that we did not anticipate, like visitors trying to figure out how well this really works. And then this was done. And the whole process from we didn't have a hip to we have the hip in the body can be done in less than a week. Basically defining the load cases, letting the simulation run, and then printing the part and mounting it into a robot. It's about 5 days of work. So that's very fast. And for us it's important because we have an agile development process and our sprints are 2 to 3 weeks. So we need fast production, we need fast iteration, and we need understanding the parts very fast. Our middleware team develops all the electronics themselves. So we have our own motor boards, which run a local PID of 2.5 kilohertz to control the motors. These are then connected through SPI to a FPGA board, which allows us to very quickly and precisely control those motor boards. And these FPGA boards then talk with each other through ROS at an update frequency of up to 800 hertz. So we can very quickly and precisely control the full robot from a PC. We get very nice force measurement. Also, at times, you could call us lazy, or maybe just smart, because we needed to measure the joint angle in the shoulder. And it's a ball and socket joint, and no one builds measurement systems for ball and socket joints. So what we did, we used 3D magnetic sensors that allow us to measure the magnetic field that is put for magnets that we put into this ball. And while we could have tried to solve this analytically, this would be very dependent on the actual placement of the magnets. What we did is we just used a neural network and learned it. So now we have a quick and fast way of finding out the net sensor position of the joint angle. Also what we've done is completely reverse engineered the Vive tracking, because it's very good, it's very cheap, right? You can get a Vive virtual reality headset for less than $1,000. And you get 2 of those lighthouses. And what we've done is basically, we built the sensors on our own and can now, using the system, track our robots just as well as we track the headset. And it's super precise, and it's about an order of magnitude cheaper than comparable systems. So that's good for us. What we're also doing is building flexible sensors, because of course when you try to build robots that are as good as a human body, they better be soft at some point in the future. And one very important thing is the skin, because it's one of the most sensorized organs in our body. In order to build and understand such a skin, we started with a paper which was published by another group, which basically used a transparent core in silicon with an LED on one side and a photodiode on the other side that measures the amount of light that goes through, and if you stretch it or bend it, this amount of light reduces. And we took this and made it 2D. So we now have a skin and you can press it. It's completely insensitive to any kind of electromagnetic radiation. It's very stable, and it gives us a very nice solution for the skin. And we're going to mount this on our robot. So in control, this is actually a hard task, because we cannot rely on existing algorithms from robotics, or only very few, because our robots have muscles and tendons, and these muscles are not motors in the joints. So classical inverse kinematics, they don't apply. So we do collaborate with a group from Chinese University of Hong Kong that's basically working towards the goal of being able to control these kind of robots in workspace. And we're doing quite well already, so you can basically control the end effector position very precisely in workspace. But also we're very much interested in learning. So this is a system which uses a very simple neural network which explores the behavior of the system and sort of discovers its possibilities. And what you see here is the system is completely doesn't know anything about its body, but it still discovers this motion very quickly and converges into it and is able to maintain it. And it looks very natural, actually. So this looks, I would look about the same. And it has no idea of where its motors are and how they are actually set in the system. Also really try to run these muscles so they generate the same net behavior as a human muscle. So basically we measure with EMG how human muscles generate force, and we directly map this onto our muscle models so as to basically generate motors that are indiscernible from muscle. So this is very important for biomechanics people, of course. They want to have physical models of the real muscle. Ultimately also we have a cognition team, because the robots need to be fun. If you bring it to the fair, it's much more interesting if you can talk to him, if you know some jokes, if you can actually react. And we spend quite a significant amount of resources in building a cognitive system. So first we integrate standard AI algorithms that are current state-of-the-art in research, like YOLO, and we sort of build one framework which integrates them all. So now we can recognize persons and objects and faces and who's talking and what. And basically this data is then accessible for other parts of the cognitive system. Also we have a dialogue manager that you really should see. It's much more fun to see it. It's a three-layered system. On the top layer we have basically a rule-based system, which is very good for fairs, because you want to be able that when someone says Autodesk that it's say something positive and cool, which of course it means. And then on the second layer we have a database where it basically stores its memory from information that it retrieved from talking through the rules and so on. We can also query DBpedia, which is a database version of Wikipedia with knowledge in a knowledge graph, and build answers on top of that. And the last layer is a generative neural network that basically learns from movie subtitles how to answer when all else has failed. So this is how you get a robot to the dawn. And from here on we're going. So we're showing the robot at the Autodesk booth at age 28, but it's just a start, right? Every half a year we have a vision that we want to achieve. So if you see Roboy the next time, after August this year, you'll be able to play the xylophone in VR, and the actual robot is going to do this in real life. Kind of switching around who's digital here. After that, Roboy will be able to pick you up next year from the U-Bahn and bring you somewhere on his bike. Then in summer, Roboy will be able to sell you ice cream. And of course, these are fun and things to achieve, but they are progressively harder for each of those skills and help us to sort of find a concise roadmap that brings us forward. And this is just a small part of it. It goes on with Roboy becoming a doctor and Roboy building himself, and at the end, Roboy should be flying to Mars, because you heard Elon wants to go there too. But if you really want to build robots that are as good as a human body, you also have to care for society. And this one thing is we do. We have an AI and ethics initiative because we see how AI and automation is transforming society, and we think it's not being talked about it enough, and we need solutions for that. But how we work is really, we work a lot with collaborations. As I said, I showed you, like the collaboration with Autodesk brought us this amazing part. Collaborations with Maxon brings us these amazing motors. With Wacker Chemicals, Soft Skin, Infineon, they're solely hardware, and so on. So we collaborate with companies using their at times not yet released software, at times not yet released hardware, and bring it into a robot to show early proof of concepts. Also, we go to fairs. So the old Roboy had more than 100 days at a fair behind him. So we have a lot of experience. That's why it's so much fun, and that's why people are crowding around Roboy. Right now, also, you can see this. We're in Hall 6, booth H28, so this hall, just about 100 meters from here. We're also part of a bigger research project. So Roboy is part of the Human Brain Project. It's the largest European effort to build the required infrastructure, so we at one point in the future understand the human brain, and we deliver the bodies for these brains to understand how our sort of control pipelines in the human body works, from cortex to cerebellum to spinal cord and so into the muscles. But we do a lot of more collaborations. So about how to intuitively interact with a robot, on how to build exoskeleton based on our systems, on how you perceive robots and what we have to do so you perceive them well, and also on how to build tissue grafts on top of our robots for later implantation. We go to events a lot as well. And not only is this a source of revenue for us, but it's also important because we go to very high-level events and are then able to talk to deciders and C-level people and tell them, oh, look, what you've seen in movies about robots, it's not true. This is not the reality. This is much more real, what you're seeing right now. This is the current status, and this is what's happening, and these are the next things that you want to consider to make sure your company actually drives safely into the future. Also, we go to schools. It's a program where Roboy goes to a school and pupils that are right before the decision of where and what to study, learn about robotics, learn about Roboy, learn about the ethical implications, and learn about where we still have a lot of work to do to build good robots. And last but not least, as I said before, we're having this AI and ethics initiative. And it's basically starting with Roboy, the actual robot, as a source of trust. So you actually believe the messages that we say. And Roboy gets a family of characters. There's Lucy, which is his best friend, and then there's a drone, which is called Checker, which is very clumsy and flies against the walls and gets broken all the time. And with that, we build a world of stories. And it's stories of young, adventurous people who use the power of technology to do something good, to use it well. For example, Katalin Voss, who took a Google Glass and developed an algorithm that's able to recognize emotions in a person. And he built a glass that makes emotions visible for autistic children so they can take part again and talk with them. And they had parents cry because their children were looking at their faces for the first time. So that's it. So this is Roboy. It's a big project. It's run very lean and agile. I think it's kind of interesting. And if you want to know more, you should talk to us. Thank you for your attention.